If you are ready, you can start.
Do you guys see the screen? Or
Yes,
Yeah.
we can see
Yeah.
the
yeah.
PowerPoint slide.
Okay, here. First one. Okay, so for my presentation, I focused on MIMO spatial multiplexing for beamforming, like my last presentation. So here's our group, and for today, I'm looking at 3 different MATLAB codes. The first one is improvement in channel capacity through spatial multiplexing in MIMO systems. The next one is spatial multiplexing in MIMO systems, but in terms of 2 nonlinear interference cancellation methods and maximum likelihood optimum receivers. And the last one, I looked at MIMO OFDM pre-coding with phased arrays in terms of spatial multiplexing, which I used last presentation. So a quick review of the spatial multiplexing. So in spatial multiplexing, they use multiple antennas on the receiver and transmitter side, and which allows for multipath components in spatial communications, which allows signals to be transmitted over multiple data channels in the same frequency band. So as a result, it increases channel capacity and does not require additional bandwidth or transmit power. And then due to the path of multipath propagation, each transmit antenna produces a unique spatial signal for receive end. And this, you can like, illustrates this on this picture. Next one. So for my first one, I looked at improvement of channel capacity. It's supposed to say channel capacity, I messed that up, but by spatial multiplexing. And in MIMO systems, spatial multiplexing is to increase the information throughput. And through spatial multiplexing, it helps separate the channel matrix to multiple modes so that the data stream sent from different elements in the transmit array can be independently recovered from the receive signal. And to achieve this, the data stream can be pre-coded before the transmission and then recombined or combined in the receiver. And so we can see this using this function I used on MATLAB, which is the product of the weights in the channel matrix that helps transmit the multiple data streams at the same time. And so this diagonal matrix, we can see, means that the information received by each array element is a scaled version of the transmit array element. So the data is being received by the transmitter, not perfectly, but it's getting the information it needs. And then because of this, it kind of behaves like multiple orthogonal subchannels with original channels, or within the original channel, and makes it possible to use other subchannels to carry information too. So for a quick summary, spatial multiplexing allows us to separate channels into multiple modes, and data that is sent from TX, the transmitter array elements, and data sent from TX array elements can be independently recovered at the receiver end, and pre-coding data can be done before the transmitter and then combined at the receiver. And then because of spatial multiplexing, there is no loss in diversity gain, and allows us to use other subchannels. So let me just go to the next slide. Okay, so for this one, we're looking at the performance of these channels, and for the blue, the plot is looking at a SISO, so single input, single output line of sight, and then the red one is the MIMO multipath, and then the yellow one is the main channel, and then the purple one is the sub channel. So we can see that since we're using the main channel, it has better performance in terms of the second instead of the second stream, and because it doesn't provide enough gain as the first stream, and since it's the less dominant subchannel, but the overall information throughput is improved compared to just single input, single output line of sight. And then this capacity of the channel can be further improved if the channel is known at the transmitter. And then with that knowledge, we can use waterfill algorithm to make the choice of transmitting only in subchannels to satisfy the SNR obtained. So then we can see a comparison over here where the red plot is the waterfill power distribution, and then the blue one is just a uniform power distribution algorithm. So for next one, I'm looking at spatial multiplexing in terms of two nonlinear cancellation methods, which is zero forcing and minimum mean square error. And then I'm comparing their performance to maximum likelihood optimum receiver. And in this scheme, the data stream is subdivided into independent substreams, one for each transmit antenna employed. And we can see that the incoming slide, we can see that the plot provides multiplexing gain, and the plot evaluates the bit error rate performance of the three the receiver schemes. And for this specific scheme, we're using an uncoded QPSK modulated scheme that employs flat Rayleigh fading over independent transmit receive links. And at the receive side, we can assume, or for this specific scheme, we're assuming a perfect channel knowledge with no feedback. So this means that it's an open loop spatial multiplexing system. So for this one, we're looking at a 2x2 uncoded QPSK system, and we can see that the maximum likelihood optimum receiver has better performance than the zero forcing or the I always forget the minimum mean square error. But this makes sense because in terms of like receiver complexity, when we use maximum likelihood optimum receivers, it grows exponentially with the number of transmit antennas, and versus the zero forcing or the minimum mean square error, which are linear receivers. So for my testing, I changed the parameters to see how if I continue putting in more transmitters or receivers, if it would change anything. And for the 4x4 uncoded QPSK system, the maximum likelihood optimum receiver is still has better performance compared to the other two. And also in the 8x8 uncoded QPSK system has better performance. So for this MATLAB code, I tried to have the scheme without any channel estimates, but I went through the MathWorks forum, but I couldn't really figure it out. So probably in the future, if I have more time, I'm gonna try to figure out how to implement this without channel estimation. But for now, I couldn't figure out the code to change it. And then for the last part, I'm looking at MIMO OFDM signal user system. So in this system, we can see spatial multiplexing in this pre-coding example, where the beamforming can be seen in each transmit and receive element, and is controlled with amplitude and phase. And for this specific MATLAB example, I was able to change different parameters such as the data stream, the number of data streams, the angle in which the array is being steered at, and the angle at the receiving end as well. I tried to change the system to have multiple users, but for this specific MATLAB, it wouldn't let me use it just for single users because it is just for simplicity's sake. And yeah. So we can see that this specific scheme uses channel coding, channel sounding, which I talked about in my last presentation, that provides the transmitter with the channel information needed for beamforming. And then so after we complete after the channel sounding is completed, we have the ability to like model the whole system in terms of the transmission and the receiver. And so my first scheme uses 16 data streams and 32 transmit antennas and 16 receive antennas in 64 quad. So for this, we can see the array geometry and the angle at which which I transmitted it, which is at 30 degrees. And at this one, you can see the receiver side of things, where it actually receives the signal given this kind of spike on here. And then this is the constellation diagram, and we can see that it has very low BER. Low BER and basically no errors. And so for this one, I try to use, I wanted to see what would happen if I changed the parameters in terms of 8 transmitters and 8 receivers, and then 8 data streams. And then I kind of steered the angle towards 60 degrees, and then the receiving angle to like 7 degrees. So here it is. For the azimuth cut, we can see it's 60 degrees over here, and then like 7 degrees over here, kind of.
Giann, 1 more minute, please.
Oh, yeah. So for my results, there was a lot of bit error rates, which makes sense because the angle at which I was transmitting the array wasn't close enough to the receiving array. So there's a lot of bit error noise. And that's what I got from when I was doing this example. And then here's my references, and that's the end of my presentation. Do I exit out?